concept, and it states that no machine would continuously supply mechanical work without some form of energy disappearing simultaneously. The converse is also true, that no machine would continuously consume work without some form of energy appearing simultaneously. So these two laws help guide us in development of machines, in producing machines, because no machine has been found to disobey this law so far. That's why it's called the perpetual motion machine of the first kind. Now, having seen that concept, the next thing we want to think about is what we call isolated systems. So we want to look at the energy of isolated systems. Then I would write an isolated system. Of course, an isolated system is one in which a system in which there is no interaction with the surrounding. So, for an isolated system, we have the Q is equal to 0 and the W is equal to 0. If we have these 2 points, this would mean that the change in E is also 0. And if the change in E is 0, therefore, the integral of the E, which is E, is equal to a constant. So that means the energy in the system is a constant. Now we want to look at closed systems. We want to apply the first law to closed systems. We call them closed or non-flow systems. If you recall, a closed system is such that no matter crosses the boundary. So we usually call those kind of systems a non-flow system. So let's look at the different types of conditions in which, and the different kinds of conditions, and apply these equations to. So, application of first law of thermodynamics to non-flow or closed systems. So the first thing we want to look at is the reversible constant volume or constant volume means isobaric process. Isochloric. Yeah. Okay, so please put a pin word here. It's not isobaric but isochloric system. So constant volume process implies zero work. Constant volume process implies zero work. Let's take an example of, say I have this again piston and cylinder arrangement. With a stopper right here. Okay, so this stopper shipping is also okay. And I have gas inside, and I apply heat over here to the system. Now, we can notice from this setup that these boundaries are what we call immovable boundaries. So, we cannot have any other work. If you notice, we have two forms of work addition, either through piston cylinder arrangement or through paddle work. So now, pause the video for a while and think about which kind of work can only be added in this system. Okay, so now you can notice that the only work I can add to this system is through paddle work, impacting momentum to this fluid. I cannot impact any work by moving the boundaries of this system. Okay, so back to our discussion. We have this setup like this. The next thing I think about is the PV diagram. So I have the P and the V diagram right here. Remember, it is a constant volume process, so I have this happening here. If you consider this setup, for example, I add heat to the gas, the pressure of the gas keeps increasing, but the volume remains constant because I force it by making the boundaries immovable. Since I have done that, that would mean there is no work in this system. So this will tell us that the work done, W, which is equal to inside the integral from 1 to 2 of PdV is equal to 0. So that means the work done here is 0. So not only do we think about this from the concept, we can also see it from the equation. Remember, we have dV as 0, no change in volume. So 0 times P also results in a 0 also. So whichever way you look at the concept, work in this setup for an isobaric process is 0. Now, if I write the equation, Q is equal to U2 minus U1 plus W. I can write this guy goes to 0. So we know that the Q becomes only U2 minus U1, which for a gas, we can write the U2 as a function of T. So we can write, following Joule's law, that U is dependent on T only, is a function of T only. So we can write that U2 is equal to CV T2 and U1 is equal to CV T1. Now, I will take the difference of these two equations. If you look at these two equations, we arrive that Q becomes the specific heat at constant volume, that's CV, times the difference in these two temperatures. That is, Q is equal to CV into T2 minus T1 for a unit mass. So I can write that U2 minus U1, specific internal energy, is equal to CV T2 minus T1. I can also write that the internal energy is equal to N CV T2 minus T1. Having done that, the next concept we want to look at is, we want to consider when this process instead of being an isochloric process that's a constant volume, we want to make it a constant pressure process, an isobaric process. Reversible, constant pressure, isobaric process. So consider our setup once more with a weight on top and the corresponding PV diagram. We have gas in the system. Now, we have the pressure of this system is held constant by the weight, but at the same time, this gas is free to expand in this volume. So, if having this setup, we can therefore write the formula using Q is equal to U2 minus U1 plus W. Now, this term is written as W is equal to the integral of 1 to 2 PdV, which can be written as P into V2 minus V1. So I draw my process on the PV diagram. Of course, we have pressure changing from 1 to 2, the pressure is kept constant at this point. So I can therefore write that Q, I'll pick it up from here, Q is equal to, I'm taking these terms together, U2 minus U1 plus P V2 minus V1. So we have U2 plus PV2 now minus, all in bracket, U1 plus PV1. If I put this, you can recall we have a concept that captures this quantity, that is H is equal to the sum of the internal energy plus the product of the pressure and the volume. That is enthalpy is equal to U plus PV. So, and enthalpy is represented by the sign, by the letter H. Small h for specific and capital H for the enthalpy quantity itself. So I can write this equation to be Q for a unit mass. Q is equal to H2 minus H1. I can also write this equation using specific heat, that is equal to Cp. In this case, I'm using the specific heat at constant pressure times T2 minus T1. Of course, the same treatment I did on the other case was, I can now write the term which is H2 minus H1 as mCp T2 minus T1. So, having those two concepts, we can therefore say that for a constant pressure process, the difference in enthalpy gives us the heat quantity. We can also look at other conditions. So, if we have reversible isothermal process, when we hear the word isothermal, we are talking about constant temperature process. We have again the concept of reversible adiabatic process. And polytropic process. So this process, they follow the same line of discussion, and you can also write their heat addition, their work done, their PVT relations, and also their specific heat. You can find a treatment. You can find a treatment of these things under the book by R.K. Rajput, Thermodynamics. You will see a beautiful treatment of these things here. So the next concept we want to look at is the concept of free expansion. Free expansion.